Hi, my name is Daniel Gottschall. I'm with the Mathematics Learning Resource Center here at Villanova, and this is my video on translating functions horizontally. So before I get into the general idea of what we mean by that, I'm going to start with a concrete example. So let's consider the function f of x is x squared. And then how would we graph this? Well, we usually pick a few points if we don't have it memorized already. F of 0 is 0 squared or 0. F of 1 is 1 squared, which is 1. F of negative 1 is negative 1 squared, which is 1. F of 2 is 2 squared, which is 4. That should be apparent since I'm squaring. It'll be the same for negative 2. And then I'm going to do a couple more. So f of 3 is 3 squared or 9. And f of negative 3, like I said, will have to be the same thing since when we're squaring, the sign doesn't change anything. Alright, so I can sketch my graph like this. Oops, sorry, that's not too good. That's a rough sketch of f of x. Alright, and then let's say I want to define the function g of x is x minus 3 squared. What would be the graph of that? Well, again, let's do some test points. So I plug in x is 0. I should have written that above, like what x values I was plugging in. It's pretty obvious for f of a g. We need to be a little more careful. So I plug in x is 0. I get g of 0 minus 3. Sorry, x is 0. I get g of 0 is 0 minus 3 squared. Uh, which is just going to be negative 3 squared or positive 9. Alright, so 0, I get all the way up to positive 9 for g. I'm actually going to do it in green. What about when x is 1? G of 1 is 1 minus 3 squared, which would be negative 2 squared, which is positive 4. If I do x's. Now, I do want to point out with alpha, I said it didn't matter if we did like positive or negative, but notice we have to be a lot more careful, like for g. So if I say x is negative 1, for example, g of negative 1 is negative 1 minus 3 quantity squared, which is negative 4 squared, which is positive 16. So here we don't have the same pattern as f, where I plug in positive or negative for x, I get the same function value. For g, it's very different. I'm not even going to graph that point because it goes too high for my uh, coordinate axes that I sketched. And actually, if I put x more and more negative, it's just going to make g even higher. You can check that for yourself, like try x is negative 2, negative 3, so on. But for that reason, I'm going to just stick with positive numbers from now on for g. So let's say x is 2, g of 2, 2 minus 3 squared, which is negative 1 squared, which is positive 1. Then finally, I plug in x is 3. I get 3 minus 3 squared, 0 squared, which is 0. So I finally hit the x-axis at x is 3, and then if I plug in x is 4, I get 1. X is 5. I get 4. That should be pretty apparent now we have enough points. I can guess when x is 6 just for time to save it. I'll say that's 9. You can check that. And this would be... Sorry, I keep missing my points. That'd be a sketch of G. And then I want to do one more example with H. When I have room here, I guess I'll do it here. Let's define h of x to be x plus 2, quantity squared. What would the graph of this be? Well, I plug in x as 0, I get h is 0, 0 plus 2 squared, which is 4. I'm going to draw it in red. For pink, I guess. When I have x is 1, I get 1 plus 2 quantity squared is 3 squared, which is 9. And as I keep increasing x, I'm just going to get larger values, which would get too high for me to graph. You can check that. So now I'm going to move back to negative numbers. When x is -1, I get -1 plus 2 squared, which is 1 squared, or 1. And then when x is -2, h of -2, -2 plus 2 squared, which is 0 squared, or 0. If I do x is -3, I get h of -3. It's -3 plus 3 squared, which comes, plus 2. And this should be a -1 squared, which is 1. I'll do just one more point. X is -4. I get -2 squared, which is +4. And to save time, I'll just tell you when x is -5, it's going to be right here, +9. You can check that. So get a sketch looking something like this. Alright, so now we're looking at the graphs of these three functions. What's really happening here? Well, if I focus on f, which is in black, and g, which is in green, I notice that in comparing the two, you could almost say, like, if I look at the x is 0, I have the point on f shifted or translated 3 to the right. Similarly here, to get to the same point on G, I have to move 3 units to the right. Same thing here, we shift this point 3 units to the right to get its corresponding point on G. And I'm doing the same thing, of course, for these points on the left. Alright. Now, why is this the case algebraically? Well, I like to think of it as we could redefine g of x, so we called it x minus 3 squared. We could also say g of x equals y squared, where y is x minus, z squared I want to use. I already used y for my plane, where z is x minus 3. But this is just the same as f of z, because that's what squaring the variable is based on how we define f. Alright, so this is how we could think of g and f being related. And then, so when we're plugging in g of 0, when x is 0, that means z is -3. So g of 0 is the same as f of -3, because z becomes -3. And we see from our chart here that that would give us 9. Similarly, when x is 1, so we're taking g of 1, that's the same thing as, so when x is 1, z is -2, so, and f of -2, again, based off here, is 4. So it's another way of thinking of applying g is just taking f of z instead of f of x. And then once we think of g and f this way, then we can see that uh, the reason g shifts or translates 3 to the right is because, like for g, x has to get up to 3 so that the graph is at the same point, g is at the same point as f was when x is 0. So what I'm trying to say is here, use a different color. I'm moving from left to right on the x-axis. Uh, when x is 0, we already have f hitting the x-axis, whereas for g, we don't get there until x is 3. So that's why uh, g is shifted 3 to the right, because it's really f of z. Like z is always 3 behind x in that sense, because it's x minus 3. I know with the minus, honestly, sometimes I get tripped by that too, thinking that, wait a minute, if we're subtracting 3, we should be shifting the graph to the left. But just think of it like that, that really when z is x minus 3, z is 3 behind x, so it takes the graph, x has to be 3 greater for z to be doing what x was. I don't know if that helps to think of it that way, or you could just notice that works for some numbers, so we can generalize it. Either way, and then the same thing here with the h's. When so we see here, oh, sorry, no, I should say the opposite. So to get to each of these h values, we're translating the graph f, in this case 2 to the left, to get each h point. And it's sort of the opposite logic with that. The reason that happens is because we can redefine h of x to be f of w, where w is x plus 2 by substitution. And this actually means, so now we're adding to x, that means our w variable is 2 ahead of x. So like here for following the x-axis, we have the h function hitting the x-axis already at x is -2, whereas the f graph doesn't hit the x-axis till x equals 0. So like when we're adding to x as our new input, in this case w, uh, it basically puts the graph ahead, which shifts it to the left. So hopefully that logic makes sense. That's the best way I can think of to explain why this happens. So in general, extending this logic, if I want, let f of m of x be the graph f of x, I'll say translated, m units, sorry, m units, I want to say to the right. Then we define, then we can, whoops, then the formula for fm of x has to be f of x minus m. This is in general how we translate a function, so many units to the right. Right, because like here, g of x was x minus 3, and we saw that shifted the graph 3 units to the right. So if I want to translate any function f, m units to the right, I have to take f of x minus m. So hopefully this video helped understanding how we translate functions horizontally. Thanks for watching. Bye.